and welcome to an introductory organic video focusing on addition reactions of alkenes. So in this video, we're going to go through all the different types of addition reactions that you typically see in the introductory organic course. Focusing first on alkenes, the whole idea about this with addition is that we are going to be adding something. But one way for us to be able to look at this reaction is imagine whenever we have an alkene, how it has a double bond. Well, we want to imagine that double bond as a set of doors that we're going to be opening up to add our different components to it. So when I say open the cabinet doors, we want to be able to redraw our structure and to add our components to it. So with all these different reactions, the big thing about them is generally the carbon structure always stays the same. We just bring along all the little hydrogens and components. Now, one other thing, what are we exactly looking at? What are we adding? Well, in this particular reaction, I am showing just X as a species. It doesn't necessarily matter what it is. We are adding X. Now, as I mentioned, we are opening up the cabinet door so that double bond opens, and we are going to be adding an X species to both sides. So we have X on the left and then X on the right. And that's the whole idea, is we're opening up the door and then adding different species. So we're going to go through a bunch of different reactions to understand that when you have this, we are always going to be starting with an alkene on the left, making an alkene as a product. So we go from that double bond CC to a single bonded C over here. And the whole idea is that when we write this, we're going to be adding two components together to make one product. So we go from two things down to one product in the end. So let's take a look at our first reaction. So addition reactions generally always have in the name what we are adding. For this first reaction, we have hydrogenation, which is all about adding hydrogen. We can see that directly in the name hydrogen. So with this one, how is it written? Well, what we can see is here, H2 is written on top of our reaction arrow, letting you know this is what we're going to be adding. Most of these reactions will have a catalyst, or in this one specifically for hydrogenation, and it's written below the arrow to let you know that there is a catalyst that is present in order for the reaction to happen. Now, as I mentioned before, this entire reaction is going to be happening where we're opening up those double doors. So I'm going to just kind of draw that double bond and just highlight where the doors are, where they're going to be opening. So first thing that we're going to be doing is redrawing our structure. So we have those three individual carbons, and then we're going to be opening up the double door, and they don't necessarily have to be pointing the same direction. We are opening it to show that we are going to be adding a hydrogen to each component. So whenever we have H2, that is telling you that we have a hydrogen being added to both sides of the double bond as we are opening that up. So as we can see, one hydrogen gets added on one carbon, one on the other, which is where our locations of our double bond were. So we add a hydrogen to both parts. Let's try another example. So in fact, we have multiple. So if we are to do these individual reactions, the same idea is we redraw the carbon structure. So we'll redraw our shape here for the first structure. And what we're going to be doing is we're opening up the location of the double bond. So the double bond here is on carbon 2 and then carbon 3. So we open it up there, and we're going to be adding a hydrogen onto each individual part. Same thing with the next chain. With this ring structure, we're going to draw our ring. We're going to open up the double bond, and we'll add a hydrogen to each part. So we can see that we're going from two products down to one. Even with this last example, we'll redraw the carbon framework. We'll even put the halogens in, the bromine and the chlorine. And it's the same idea, is that we're going to be opening up that double bond and just highlighting all these just so we can see it. We're going to open that up and put a hydrogen on each individual part to show how the doors are opening, right? We're adding our group onto the carbons participating in the double bond. So whichever structure we're looking at, whether it's the first one, right, we have carbon number 2 and then carbon number 3, those are going to be participating in that opening. Let's go on to our next reaction. Our next reaction type is halogenation. And from this one, you can see the same general premise. It gives you the name inside of saying ation, right? We're adding something. So in this case, we're adding a halogen. So halogens can be chlorine, fluorine, iodine, bromine, any of those individual species. So usually we denote that with the letter X, and that can represent any of these major halogens. So for this one, it's going to follow the same idea of hydrogenation. We open up the double bond and we will have a group on each of those individual carbons. So just kind of label those carbons, right? So we have one carbon here in red, the other one in red as well. And we can really illustrate that that is what's going to be opening. So we will redraw our structure and we are going to open up the double bond. So we'll put one on carbon 1, one on carbon 2. And being that we're adding chlorines, there will be a Cl on each individual structure. So we're adding to each part. And it might be a common thing where you even might have to name it and go through naming rules, or even go farther. So this video, we're just going to particularly show is how we can add these little parts. And if you want to, you can always try to clean up your structure as well. So for example, we can show that, okay, we're adding our little chlorine with the methyl group, so it looks a little bit more like a correct geometry as well. Let's try some more. So with these particular geometries, same idea. We're going to be copying down the main structure. So here we have our chain, and as before, like I mentioned, we have our double bond. So this is our door that we're going to be opening. So we will add one on this carbon and then one on the next carbon to show, okay, we open the door and we're adding a bromine to each portion. For the next one, we are adding iodine to our cyclohexene. So in this case, what we're going to be doing is we are going to be adding our cyclohexene to our double bond here. We are going to be opening up that structure and then writing an iodine on each portion of this species. And notice how it went from an alkene to a cycloalkane with halides on it. So it's an alkyl halide that we're changing the functional group along with it. So the carbon chain always stays the same. It's the functional group that is changing. So same thing with this last example. We are going to be opening up our double bond. We will leave our bromine and our chlorine that was originally there, and we're going to be adding fluorines to each individual part of the double bond. So we're going to open up those doors and add our pieces. And this is the whole idea with these types of reactions that involve the same species. So we have H2 or F2, Cl2. They all have that diatomic characteristic. Now let's go into something that is not a diatomic and is more of a heterogeneous species. So hydrohalogenation is when you add a hydrogen and a halogen, meaning we have two different species, but it's still going to be following the same general idea. We're going to be adding both components. However, one thing you're going to quickly realize is, well, if I'm adding two pieces, so we're going to be adding a hydrogen, and why don't we color code these? So let's say if we add a hydrogen in blue and we'll add a bromine in red. Well, the same idea is that we're going to be opening up the double bond. However, what side do you put each species on? Because if we were to draw this structure, we can see that, all right, well, we'll have one species where we can put the hydrogen, let's say, or the bromine, let's say, on the left, hydrogen on the right. And if we were to redraw that, we could also write it where I could have hydrogen on the left and bromine on the right. Now, the question is, well, which one is true? We have two different options of products. So what we actually have to do is we have to be able to predict the correct or the major product that is formed within a reaction. So how exactly do we do that? Well, we're going to go off the following rule. So the following rule is all about, it's called Markovnikov's Rule. It's one of our few rules that we come across in introductory organic, which is a scary long Russian name. So with Markovnikov's rule, the whole idea behind it is that hydrogen wants to bond near hydrogen. So the way I like to view it is that hydrogen wants to make more friends that are just like hydrogen. Hydrogen is a social butterfly that likes to bond to another species. So if we have our example from before, well, we had two different products. How did we know which one is the major species? So what it comes down to is going to our original reactant. So if we go to this reactant, we are looking at the double bond. And like I mentioned, hydrogen wants to bond near more hydrogens. So what we're going to do is we're going to look at both carbons, the one on the left and the one on the right, and count our hydrogens. So how exactly do we do that? Well, let's take a look. So if I'm on the carbon right here, well, how exactly do I go about trying to count carbons? And let's pick a different color other than yellow. So let's redraw that. So if we have, let's say, our carbon right here, how can we decide that? Well, we have one bond here, two bonds, and then three bonds all around this carbon. So how much room is there for hydrogen? Well, we can fit a total of one more hydrogen on this carbon. Now, if we look at the other carbon, which I'll draw in purple here, well, what can we do if we zoom in on that? How many bonds are around that particular carbon? Well, same idea as before. We're going to count the number of bonds it currently has. And we can see that we have 1, we have 2 for our double bond, 3, and 4 for the single bond. So is there any room for hydrogen? And if you remember, carbon can bond up to 4 things. It already has all 4 bonds. So for this one, well, we have 0 hydrogens on this carbon. So we have 0 on this side, and then we have 1 hydrogen on the left. So what is going to happen is hydrogen wants to be with other hydrogens. So the correct structure is going to be this bottom one, which showed that hydrogen wants to be with its fellow hydrogens. So both of them are going to be there. It is happy. It has its friend. So this is what we refer to as the major product when it comes to the Markovnikov type of reaction. Let's look at some further examples of this. With this example, we're going to be taking the following alkene and adding HCl to it. So what do we have to exactly do? Well, it's the same idea as our hydrogenation and halogenation. We just have an extra rule to tell us which product is the major one. So we're still going to be opening up our doors around our double bond. So let's highlight the double bond to show where everything is going to be happening. Now, with this structure, what we have to do is we need to count the number of hydrogens on the right carbon as well as the one on the left carbon. So if we are to look closely, well, on our structure, if we are to look on the left-hand side, well, how many hydrogens do you have? Well, what you have to do is count all of the bonds that are currently there. And we can see that we have 1, 2. So remember, every carbon needs 4, so there are 2 hydrogens on the left one. We're going to do the same exact thing on the right-hand side. So when we do that, we are counting our number of bonds, and we can see that we have 1, 2, 3, 4 all around this. So there is 0 hydrogens on the right. So when we open up our doors, which side is it going to be going on? We can see that's going on the left-hand side of our door. So we are going to redraw our structure, right? So we will have that just like so. We're going to open up both sides, right? So we're opening up those doors, and hydrogen is going to go on the right-hand side with all of the other hydrogens that are a part of the structure. So let's show that in maybe in blue, just to kind of show that we have the two original ones. And then chlorine is going to go on the right-hand side. So hydrogen went with its other hydrogen friends when we opened the door. Let's go on to another reaction type that you're going to see. The last reaction that we're going to come across in addition reactions is the hydration reaction. And what you can get is, well, what is it when you hydrate is you are adding water, right? So stay hydrated. And what happens when you add water? It creates an alcohol. Now, with most of these, it typically happens under an acidic condition. So very commonly, you'll see H plus written here, maybe H2SO4, HNO3, some sort of strong acid to tell you that we are trying to create an acidic environment. So when we're adding water, what components do you have with it? Well, it comes down to understanding what the structure of water is, which is H2O. Now, if we were to break one of the bonds of H2O, we can see the two parts. So let's just say if I broke the bond right here. Now, with that, we can see that we have a hydrogen as one part, and then we also have an OH as our other component. So we are going to be adding a hydrogen and an OH, and it's still going to be governed by the Markovnikov rule because we have two separate different pieces. So same idea as before, we're going to go through this. We can mark and draw our double bond, right? So this is where our doors are going to be opened in our structure. We're going to open the bond. Hydrogen is going to be added to the side with more hydrogens. So let's illustrate our hydrogens. On the left-hand side, we have two hydrogens. On the right, we have none. So where is hydrogen going to go? It's going to go on the left side with more hydrogens. So when we draw that structure, we will redraw it again. We'll draw the same carbons, but the only difference here is we're going to be adding one hydrogen to the left and then our OH group on the right-hand side, creating an alcohol, right? So we are showing that tertiary alcohol where it's making T-butyl alcohol for our product here. Let's do some two more, and just so we can make sure we understand Markovnikov rules and hydration reactions. Now, with this one, it's the same general idea with the first one here. We are going to be opening up that double bond. We are adding H and OH are our two components that are going to be added. Now, where do they exactly go? Well, we have to look at our structure and count all of our hydrogens. So if I look at the carbon on the left-hand side, well, we can see we have 1, 2 bonds, 3 bonds. So that means there is room for, so that means there's 1 hydrogen currently here. Now, if I go on the right carbon, well, we can see if we count all of our bonds, we have 1, 2, 3, 4 bonds. So that means that there is 0 hydrogens on the right-hand side. Okay, let me spell out the word 0 because I keep thinking it looks like an OH. So we have 0 hydrogens on the right-hand side, 1 on the left. So when we draw our new structure, when we open up our double doors, we're going to be putting 1 hydrogen with its friend. So it's just going to go over here on the left with its other hydrogen. And then the OH is going to go right in the middle of our chain away from that hydrogen. So hydrogen wants to go with more friends. Now, with some structures, Markovnikov rule does not always apply. So for example, with the following structure, if I count all of my bonds, I can see that I have 1 hydrogen on the left, or sorry, the top, and 1 hydrogen on the bottom. So there is not a preference. It has to be whenever, usually it's when there's branches involved or other functional groups is when you see that you're going to have to add something special to it. So you always want to count your hydrogens to see what's on both sides when you are going to go for your final result. So once again, we're going to open up those double doors and we're going to be adding a H and an OH. And for this structure, you could draw either one. You could write it where it's H on the bottom or OH on top, because they are the exact same structure, right? You can flip them and they will be the same. So they are the same. Okay, so both exist. So it has to depend on really what type of reaction you have with addition. Hopefully this video helped to go through all the different concepts. Please check out other videos on my introductory organic series, and there's going to be a lot more to come. This has been Dr. Dan. Thank you so much for watching. Please hit that like and subscribe button, and I hope to see you all in the future. Bye now.